welcome to Wireless Future. My name is Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm doing fine. How are you?
I'm good, thank you. So I realize this is episode 22. Is that correct?
I think so.
You think so? Yes, I think so. So we've been doing this for I think it's more than a year now, isn't it? Wow, that's
second season,
amazing indeed.
double 2 in the number of episodes as well.
Oh yes, it is indeed. All right, so the discussion I will be having today is going to center around some aspects of antennas and antenna arrays, and specifically the notion of being in the near field versus being in the far field of an antenna and of an antenna array. And this is a rather, technical and intricate topic with a lot of terminology indeed, and which also requires a lot of rigor. When really, or requires put it this way, it requires a lot of hard work to do rigorously from the first principles in electromagnetics. So perhaps we could start on the question of terminology here. What is the near field really of an antenna?
So this is an area that I have spent quite some time on thinking about in the past few years as well, because just as you're saying, it is an intricate topic to go into detail in, and therefore most textbooks are also a bit glossing over the details because they probably didn't want to focus on those things, but then there are still reasons to consider it. And now people also in communications considering the near field, and for that reason I think it's an important topic for the future. So to answer your question, what is the near field? So when you have an antenna, it is essentially an object with a distribution of currents over its surface, and that is then creating an electromagnetic field that you can measure. And you can use Maxwell's equations to compute the electrical field at different locations. But we like to make simplifications to figure out how we can describe it in a more convenient way at different distances. And very close to the antenna, you have the reactive near field. In this case, you can both measure radio waves that are on the way to travel far away, and you can measure sort of an electric field that is just around the antenna, or magnetic field as well. So you can think about it as the electric field that is existing around the coil. That one is measurable if you are really near. Then if you go a bit further, you are in the radiative near field. Then this reactive part that only exists around it, that doesn't really travel away, they are negligible. And in the reactive near field, you still have certain properties that if you are measuring the strength of the signal in different angular directions, it varies depending on what the measurement distance is. Of course, it always varies in strength, but the distribution over angles varies. And then if you move further away, then the antenna will look so small from the point where you're measuring, so that it's only the angle that determines the distribution of the strength of the electric field over the different angles, and not the distance.
Yeah, I think it's rather consistent with my understanding as well. Is it correct to say? You could, if you have an antenna, right? You could expand the electric, or the magnetic for that matter. But let's talk about the electric field, which is time varying. Then obviously you could expand that in terms of some of different components, and some components decay inversely proportional to the distance, and some decay faster, right? Like 1 over r, if r is the distance, and the next decay is 1 over r squared, and so forth. So
yeah,
is it correct to say that we are in the far field if it is a good approximation to retain only the first term in this expansion, namely the one that goes as 1 over r, where r is the distance?
Yes and no. So when you are only retaining that first term, then you have left the reactive near field. So these things that only exist around the transmitter can be neglected. But depending then on how large your transmitter is, you will or will not have this kind of thing in between. the reactive near field and the far field, which we sometimes call the radiative near field, sometimes the Fresnel region. And this is really if the antenna is physically large or much larger than the wavelength, then you can see these field variations over angles for a certain number of distances. And there is something called the Fraunhofer distance, which is determining approximately how far you need to be before you can neglect even those effects.
Yeah, so, I have to admit I had to dig out my college textbook in electromagnetics here to feel like well prepared for discussing this topic. And it's the Helden-Marion, I believe it's actually a second course on electromagnetics, and it does have a discussion of antennas, obviously, and dipoles and linear antennas and also other structures. And it does also discuss the Fraunhofer limit that I think you alluded to here. And then it does say in a footnote that antenna engineers often name this the far field criterion, so referring then to the Fraunhofer limit. Often name this the far field criterion and express it as a tolerance of r greater than twice the distance over lambda, or twice the antenna size over lambda. Many authors do not distinguish carefully among the limits expressed in equation 962, which is, I think, what you're after here with these two regimes, right? In particular, there is an ambiguity in the use of the terms far and near. In optics and antenna engineering, these words usually refer to the Fraunhofer test, to which we return in chapter 12. But in discussing the field of an oscillating dipole, we use them to refer to the radiation test. So I think it's really hard to accurately state these points without using like mathematics and figures. But for let's say casual listeners, the take-home point might be here that you're going to be very careful with terminology. And there are, two different regimes that you can be in, right? When you're like close or far away from an antenna, you can be in the reactive near field, you can be in the radiative field, you can be in the far field where the Fraunhofer criterion applies. And to make matters worse, I think ubiquitous use of antenna arrays in modern comm systems and radar, obviously, for that matter, adds, I think, on top of this confusion, right? Because some authors use the term far field and near field here for an array to actually refer to something else, which is not a property of the individual antennas themselves, but rather a property of the antenna geometry. And I'm not sure whether I coined the term. I don't believe so, but I couldn't, on the other hand, pinpoint where it comes from. But I think when we discussed earlier, I used the term geometric far field when speaking about an array to mean the regime where you can consider the waves from the individual antennas to be plane waves, right? So now when we have an array, then there is, on top of the terminology that we have for individual antenna elements, there is now going to be also the question of whether the wavefronts from the elements in the array can be viewed as planar or not. So viewing the whole array as like a single antenna, more or less, right? And then computing the Fraunhofer limit. So maybe you could elaborate on this, Emil. And I mean, and also in a way, I mean, these terms here are like, I think this book here is probably written in the, I don't know, maybe 60s, or maybe it's actually more recent, but I think the first edition came out long ago. Yes. 65. So these are like well-established theory, right, and terminology for the time before we were even born. But is it like a new aspect or a futuristic aspect now to all of this, now that we build these massive MIMO arrays and so forth?
So yes, there are, and even so one difference which we will come into is the difference between what is important when you're only studying antennas and what is important when you're studying the communication usage of antennas, where we sort of need to expand the terminology. But also within the antenna community, yes, there is rigorous definition, but those have also changed over time what we are considering. So if you read papers from the 50s and 60s, they are describing the world a bit like I did from the beginning with the radiative, reactive, the Fresnel region, and then the Fraunhofer region or far field. But then that was based on the idea that all antennas will be focusing its radiated signals at a point that is far away. And then we are studying what happens at different regions. Then we realized we can also build antennas that are focusing the signals at a close by point. And then some of these zones doesn't exist, or you can control whether they exist or not. So there's a lot of issues. But so IEEE have even changed their terminologies between far field and near field over time as well in the antenna community. But as you were pointing out, the arrays are getting larger. So for that reason, it becomes important to go back to these definitions and see when are the approximation that we did in the past still reasonable to do, and when does it change? And also, as you were mentioning, this Fraunhofer distance is you take 2 times the longest distance of the antenna, like the diagonal of it, you square it and divide with the wavelength. And as you make the wavelengths smaller and smaller, you also get a larger Fraunhofer distance, which means that you have a bigger chance of being in something that is not the far field.
And when you say not the far field here, you mean really the far field of the combined array and as a radiating structure, right? So referring to the...
So I'm thinking about the aperture in total, because if you go back in this 1950s, 60s papers, they are mainly talking about you have an aperture, an antenna of a certain dimension, then there is some kind of variations of the currents over that surface, and that generates a radio wave. And then how you would actually create that variations of currents over the surface, probably with an antenna array where you divide into discrete elements, but they are more interested in the continuously varying case, which might not be possible to build.
No, but that's what I meant. I mean, we're considering the entire array as the radiating the antenna here.
Yeah.
Is it like, I mean, there seems to be like a bit of revived interest in looking at the electromagnetics and specifically at the effects here that concern like being in the near field and far field and so forth. And my understanding was that, I mean, this is because we're going down in wavelength, right, up in carrier frequency and building larger and larger arrays. There's this obviously massive MIMO. There's also this talking about ultra large and extremely large arrays and so forth. So what distances are we talking about here, like concretely, if we pick like, I don't know, some frequency band that is used for communications or foreseen for communications, and some distances in meters? Do you have any like insight to give on that?
Yes, so it depends on what kind of properties we also want to measure, but say that you have an array which is, 1 meter and you're communicating at the 3 GHz band, then the Fraunhofer distance might, is actually not the Fraunhofer distance, we can come back to that, but the places where new interesting communication phenomena appears might be like 2 meters. But then you make your array 10 by 10 meters, and since this distance is pushing with the square, well then you have 200 meters, and then you go from 3 gigahertz to 30 gigahertz, and then you have 2 kilometers. So we can have different distances that are mattering here. But I think what is important to remember is that these definitions for far field and near field from in the electromagnetic or in the antenna community, it's only a concept that can be measured from a transmitter. You are measuring at different distances and you see what kind of approximation you can do about how the wave looks like. But from a communication perspective, we want to have both a transmitter and a receiver. And since the definition is sort of describing how does the field look like at a particular point, then it's natural that at that point we put a small receiver. And then we look at, okay, we have a big transmitter, we have a small receiver, how does it depend, the channel depend on how we move around the receiver. And then we have the reciprocity that says that the channel should be the same in both directions. So then we can swap the order and say we have a small transmitter, we have a large receiver, and then the same phenomena should appear somehow. But in that case, which doesn't really make sense from an antenna perspective because we don't define things like that. But from a communication perspective, it makes good sense. And then what really happens is that over this large receiver antenna, you will be able to see wavefronts that are spherical. Of course, waves are always spherical, but if you have a small receiver at a large distance, we can approximate that almost being a flat wave that's coming in. But if it's large enough, you can see the curvature, and you can potentially also see variations over the amplitude over this antenna.
So, but do we really have to worry about all of this? I mean, so suppose we have an antenna array, right? No matter it's used for transmission or reception, and then we're communicating with a mobile, say, out there. And as long as the mobile is in the far field of each individual antenna in the array, isn't it that, like, well, we can model to a reasonable degree of accuracy the channel between the mobile and any of the antennas in the array as a linear time invariant, or at least a linear system, and then we can apply the usual stuff. I mean, using reciprocity preferably to estimate this, I mean, the impulse response of the system, and then transmitting waves using Carnegie beamforming, for example, just add up constructively, right? I mean, this is the basis of how modern MIMO works, and whether or not this mobile is in the far field of the array doesn't make a difference in any respect at all. I mean, well, the story is a little different, I suppose, if you were to like estimate or use the notion of angle of arrival, or even use the array for positioning, I'm not sure. But if we just talk about like communication using reciprocity-based MIMO, I don't think it matters if you are in the near field or far field of the array, as long as you're not in the near field of an individual antenna, because then all sorts of odd things start to happen, right, with coupling and so forth. Is that a correct understanding, you think, or is there something else here that we ought to think about?
So as long as you have protocols that are using reciprocity-based beamforming, you just estimate the channels as it is, and then it will work out for a single communication link. You don't really need to care so much about what happens. But there are other reasons, as you were alluding to. In many cases, people like to use geometrical models, and when we talked in the previous episode about coverage without beamforming, and then a common way there is you want to send different angular beams in different directions, and those angular beams are only appearing when you are in the far field. And closer than that, the beam haven't really started yet. So one can say that approximately at this Fraunhofer distance divided by 10, this is when the beam starts to appear. Then it's like 3 decibels or half the strength that it would have further away. And that's actually a good point. I mean, this whole notion of beam forming, right, where you know, like you see in the papers and even in books, I guess, with you know, some colorful like beams that point into different directions. Then very often that's a misrepresentation of what's actually going on. And as you said, you have to be very far away from the array to actually see these beams. And how far away they have to be can be expressed in terms of this Fraunhofer limit or distance, where you plug in the array dimensions then rather than the dimensions of individual antenna elements, right? But now this whole notion of being in the far field or near field of the array is only important if you want to do like geometric models and talk about beamformings, talk about like angle of arrival and so forth. If you just do the like canonical multi-user MIMO precoding like we do in like massive MIMO, then there's really nothing to be concerned about here, I think. But of course, as you said, I mean, some folks like to use geometrical models for different reasons. I think locally, say, positioning is one, right, where you want to estimate like the direction to the mobile from your access point and so forth. So, but there are some other aspects that are still of interest. So if you then are applying this reciprocity-based beamforming to someone who is much closer than this Fraunhofer distance, how will the signal look like if you start to measure it around in space at different locations? Well, you will create something that we could call it a beam. Locally around the receiver, there will be a stronger signal. It will have a beam width that is spanning perpendicular to the direction where the signal is going, and there will be and this is the interesting thing, a finite depth of the beam. Usually it sort of starts at a certain distance and then you can measure the beam until infinity. But just as when you are focusing a camera at something that is close by, it gets blurry behind it. The same thing is happening when you're focusing the signal. You get a finite depth around the receiver where you get the strong signals. And it becomes a bit more like a lens. You you're focusing the signal as a ball or something around the receiver. And I think this is important for several reasons. One is that you are, this says something different about how you could multiplex users. Even in line of sight scenarios, usually it's like, okay, in every angular direction we can serve one user, and if they are overlapping an angle too much, well, then we can serve it. But now they can also be in different distances, but in the same angle, and it will still work out.
That is absolutely true. I mean, again, and it refers to this notion, or rather the misconceptions around the notion of what a beam is, right? I mean, I maintain that it's in many cases grossly misleading to think of beams the way they are depicted in lots of papers and books. I mean, some pointing in a given direction like this. To start with, like you said earlier, you have to be quite far away. I mean, on the order of the Fraunhofer distance corresponding to your array, you have to be that far away from the array to actually see anything that resembles a beam. So
I can point out one more thing that is also of relevance, and that has to do, of course, with channel modeling. That we don't need to care about the channel model when we do reciprocity-based beamforming, but when you are in the near field of the array, so to say, or the radiative near field, then different antennas will see a different amplitude of the signal, even in a line of sight scenarios. Not due to fading, just because you have so large variations in the distances that you can measure these amplitude variations, and that will require you, particularly when you're very close, to model the antenna or the channels in a different manner. And it could also be that now the array is physically large, which means that a smaller object can block part of it. Sometimes we call this non-stationary, spatially stationary channels, where some parts of it is blocked but not other parts of it, for example.
No, that's a good point indeed. I mean, that somebody, say, rather simplistic channel models that lots of papers or academic papers are using, right, with independent Rayleigh fading, correlated Rayleigh fading with clusters and so forth. These break down once you are in the, I like to call it the geometric near field of the array, but I'm sure it is like an established really terminology. You said you just said near field, I think, but you really meant the near field of the array, right? Yeah. But other than that, I mean, is there anything else that we will like either keep in mind, or that would prompt like a redesign of anything that we know, or any like signal processing algorithms or anything based on understanding better the electromagnetics, you think?
If you rely on geometry, then you need to redesign things. If you have channel models, if you are used to using very simplified things like Rayleigh fading or line of sight scenarios, then you need to consider, in the line of sight scenario, now things will also depend on distance. In the Rayleigh fading scenario, since the geometry is different, you will have a correlated type of fading, which is factoring distances and geometry and things like that as well.
Yeah, it easily becomes complicated here, right? So, but is there really a reason to rely much on geometry? I mean, I understand obviously that if you're in like free space and you have some antenna array of any arbitrarily complicated shape and elements that could be anything more or less. I mean, in principle, you could use numerical methods to compute the EM field at any point, and you could optimize your beamformer and so forth for that, right? And you could call that geometry because it's all based on like starting off from geometric model in 3 dimensions, or 4 actually with time then, but then solving like Maxwell's equations or approximations to Maxwell's equations. But in reality, we're always going to have like reflections. I mean, there'll be, to start with, there'll be a ground reflection, right? And then there'll be scattering, and there'll be all sorts of objects, and these can't be modeled very well using geometry. I mean, I think that's one of the things that we have like realized in the in the comms theory community in the last 30 years, that it's very difficult. I mean, even you have something you think is line of sight, but you still have like some reflecting paths and multipath and all sorts of things going on in your propagation environment. So the question is really, why would you want to rely on geometry to start with? I mean, if you do like reciprocity-based beamforming, there's no point in fact, knowing something about the geometry doesn't really help much at all. And if you insist on like beamforming in the sense of shooting power into different directions, I think it's really it's probably the wrong way to go. I mean, it might be better than to use some kind of maybe a machine learning algorithm that can discover what the environment looks like and then like infer implicitly how, you know, received field or observed field relates to transmitted waves and so on. Or do you have a view on that?
I definitely agree with you that from a communication system design, we want to utilize as little about the geometry as possible, because there's always the danger that we're then adding a prior to our design that doesn't really hold. From a localization perspective, as you was mentioning, then we are used to really utilize strong geometrical models to estimate angles and things like that, and there. Yeah, since usually localization works the best in line of sight scenarios, it could be a chance that it can be useful to do it there. But it definitely is a challenge for a particular reason that you're mentioning. And why have I spent several years trying to learn these things better now? Well, I think what I'm after is to understand more of the fundamental limits. So one thing that we like to say in massive MIMO array is that as you add more antennas, you are increasing your signal proportionally with signal power that you receive proportional with the number of antennas, and eventually that trend needs to break down when the array becomes very large. And I wanted to understand how precisely that happened, and that is one of the things I've been analyzing.
So how large is large, right? I mean, what does infinity mean here? Like, obviously, when you think of like a uniform array or whatever shape array, and you just grow it bigger and bigger, then it's like if you just apply the textbook MIMO formulas, it's like the received signal to noise ratio would grow to infinity, right? Which is obviously makes no sense. And then the question is, how large can the array become before like that argument breaking down, which is going to relate to how far do we need to be away from the array to stay in the array far field or geometric far field and perhaps and so forth. But also, I mean, relating.
There I have a concrete answer actually. So what is the answer? So when the distance to the array is shorter than twice the longer side of it, then you see that you need to measure the channel gain or array gain in a different manner. It starts to taper off because of three things. You see the different angles from different elements in the array from different angles, which is sort of reducing their effective size. The polarization of the wave will interact differently with the antennas, and the third thing is just that you have different distances, so that creates different amplitude losses over there.
Right, and these three things all happen approximately at the same point or distance.
They might kick in at different distances. It's hard to separate them exactly, but I think the polarization, for example, happens much closer by. But at twice the longer side of it, that is when you should start to expect different array gains. While between that one and up to this Fraunhofer distance, you should just be careful with using geometrical models, but as long as you do your beamforming correctly, you will get the array gains that you want to.
Also, I mean, relating back to your point about positioning here, it's certainly true that you can do positioning based on geometry, right? Like estimating angles and so forth, but lots of methods are also just based on fingerprinting. So you estimate the channel impulse response, and then you match it with a database, which could be like an artificial neural network or something, I suppose. It's the most modern thing there to do. In which case you don't need assumptions on the geometry. But certainly if the geometry is accurately known, then you could, of course, exploit that knowledge. So, So another thing here that comes to mind, because we spoke now of a little bit about individual antennas, right? And we said that there is the reactive area or reactive near field, and there's the radiative field, and there is the far field, when you're beyond the Fraunhofer limit. And then we talked about arrays, and so that, well, for arrays there is also a corresponding Fraunhofer or far field distance associated with the array itself, right? I mean, treating the array as, well, just a radiating aperture. But now talking about like near field effects, there's another thing that comes to mind here, I think, and that is mutual coupling, because the difficulty here is that if you have like more than a single antenna, so you have two antennas and you put them close to one another, then they start to interact, right? And this is a rather toxic thing, which is quite well understood in the electromagnetics literature, but unfortunately often ignored in many COM theory papers, say. And I guess it's been one of my stick courses, but if you build an antenna array and you keep your antennas at least half a wavelength apart, then very often typically you can ignore coupling effects. If you push them closer, then you very quickly reach a regime where coupling becomes the dominant phenomenon, and where almost everything you have said becomes, wrong or inaccurate. And this is true even if you just play around with like point sources, right? I mean, think of a scalar field and you put point sources along a line, so like a linear array of point sources, and you put them at half a wavelength apart, then and they generate, each one of them generates a field, which could be like a pressure field, let's say, in a scalar field then. And then you put a sphere around the whole thing, and you integrate the power density of the pressure field around that sphere. Then you'll get the sum of the squares of the input power to each one of the sources. But once you push them closer than half a wavelength apart, even that breaks apart. So this is a rather complicated thing, which I think is, unfortunately, in the COM theory literature, sometimes mistreated. And it's not hard to find papers and arguments that build upon like assumptions. Okay, let's push the antennas closer than half a wavelength, and then pretend that, what we call power in the information theory and signal processing, which is like the norm square of a signal vector or something like that, that what we call power actually has anything to do with the physically radiated power, which it well, it does, but it's not an equality. I mean, they aren't equal, right? So is there something here that we should take home, you think, in addition to what I already said? Or because we got to keep this in mind, right? When we speak near field, we also speak coupling, I think.
Exactly. So if you go back to the kind of papers that were published in the 1950s and 1960s, where people were looking at apertures with arbitrary continuous variations of the currents, and from that one you can compute what kind of radiated fields you are getting, and of course what you have in the near field as well. And I think that kind of theory is taking all kinds of effects into account. The question is rather than how do you build something that can generate that kind of current variations over the aperture in reality, and then we start to divide it up into small elements because we know an integral can be discretized into summations, and then every term should be independent, right? And then the danger comes that no, the different antennas are not independent of each other. So if we are designing our system to generate a certain say current in one antenna in separation, and then you put them all together, you get a different current distribution over the array. So this is really one of the engineering issues that comes between the antenna domain and the communication domain. And yes, I think that what the results in communications in terms of performance is probably achievable, but maybe not using the models or the type of antenna arrays that are used as assumptions in the communication area.
Yeah, again, I mean, lots of things happen, right? When you take coupling into consideration, the most important thing is that the some of the signal squares, which we call power in, let's say, applied information and COM theory literature, is not any longer equal to the actual radiated power from the antenna. So I think a safe place for COM theory papers that put antennas closer than half a wavelength together without rigorously considering or modeling the electromagnetics, I think, is probably the trash bin. Do you agree, or you think there is still something like in here?
I'm not entirely sure to what extent the result are still indicative of the right kind of result and in which situations, but I think definitely it is an area of concern, and I think this is one of the reasons why I am going back into this area and try to find a stronger link between the antenna community and the communication models that we are using to get rid of these kind of effects. And
but the thing is that these effects are so strong that or so large, right? Some time ago, I also spent some time trying to understand better, even with scalar field and point sources, what happens when you push them closer than half a wavelength, right? And then even just computing the impedance matrix and the radiated power. To do that, once I pushed the antennas closer, and I think it was like 0.4 lambda together, I had to download this arbitrary precision floating point package for Python in order to even do the numerics, which kind of gives an indication of how extremely ill-conditioned things are and how extremely large is the discrepancy between what we call power in the COM theory papers and what's actually power in the physical world, right? So, anyways. I guess we could continue on that topic for long, but maybe we should also move on. And, staying on this now near field regime, right? Even let's talk about an individual antenna again. And, being in the near field or even in the reactive near field, can that be useful? I mean, I suppose there are these contact or communication schemes that actually rely on coupling, right?
Indeed, this is one of the maybe most commonly used technologies today, and sometimes it's called NFC, standing for near field communications, but more often we are just thinking about it as RFID or radio frequency identification, like the tags that you're using to open a door, for example, or maybe you're using a Metro card which you're just holding against a reader and then it's open up. It's sort of the same type of technology there, and these things are based on the magnetic coupling that are happening in the reactive near field, with the reason that many of these tags can be completely passive. So they contain the circuit, you hold it close to something that is creating a field, and then you are, based on that field, you are modulating it, changing the load in an active manner to communicate signals back to the transmitter or sender there.
So you're actually now located in the closer than the radiative, in the reactive, in the reactive near field.
Exactly.
And you're actually exploiting the coupling, right, for communication.
Exactly, so. And many of these technologies are working in the megahertz, or hundreds of megahertz, or maybe down to 100 kilohertz or something like that. So then the wavelength is very long. And the intention is that this technology should only work over, say, up to 4 centimeters, so that no one should be able to read your card from the other part of a building or something.
Right.
So from that perspective, they are meant to only work over very short distances. And many mobile phones nowadays are also supporting this, but more in an active mode, that it can mimic how a NFC tag would work. So if you store your Visa card in your phone, it is essentially behaving as if it was the Visa card that you have in your wallet. But while the one in the wallet is a passive circuit, the mobile phone is sort of synthesizing the same kind of things to communicate with the reader.
Right. So we should be glad that the reactive near field doesn't extend too long, then, so somebody could snatch your credit card number from a longer distance, right?
Yeah, but of course you can always put up a large receiver and be able to measure things from a longer distance also in these kind of cases. And I think if you like me like to be part of like running competitions, then often nowadays you get a kind of reader that you either put on some number tag on your clothes or you put on your shoes, and then they have a big reader that is able to read like a tenth of people simultaneously who is just running through some kind of obstacle. And the technology can handle many things, so you can make big receivers so that you can handle reading on many tags at the same time.
Yeah, it's amazing. Wow. So I guess we spoke about antennas, and we spoke about arrays of antennas, right, communicating with like a mobile or something. And then I guess mostly throughout here, the kind of starting point in, or at least a mental picture I think we both had probably, was that mobile had a single antenna and that was it, right? But I also suppose that, especially now with like millimeter wave and terahertz and all that, both sides will be using large arrays, or arrays at least, right? Potentially large arrays. And I mean, large here could mean like number of elements, and at like very high carrier frequencies, even a large array with many elements, it doesn't have to be physically large, of course. So is there anything here among what we have said that would like change, or would have to be like considered differently if we have arrays at both sides of the link?
Yes, then you can do new interesting things as well, or maybe they're not new, but you can use it in situations that you couldn't before. So if we start from having a transmitter with just one small antenna, and then you have a large receiver, you see the sphericalness of the wavefront, and you could potentially also see the amplitude variations over the array. And while the amplitude variations are only depending on the distances, so it's true geometry, the phase variations that are sort of showing the curvature, those ones are wavelength dependent, because moving a certain distance means much more of a phase shift at higher frequencies when the wavelength is smaller. And what that then means is that if you now have two antennas at your transmitter that are sufficiently far apart, you could essentially observe the different curvatures from these two different transmitters at your receiver side. And conventionally, when you have a line of sight communication system, no other paths, then if you use one polarization, you can send one stream of data at the same time, and you cannot tell anything else apart. If you use dual polarization, you can tell two apart, but then there are not more polarizations than that. But now when you also can utilize the spherical wavefronts, you can actually send multiple streams over the same line of sight paths. You don't need to have any reflectors or anything that create additional paths. You can do MIMO communications with many streams or layers or whatever you want to call this, parallel signals over this, as long as you are sort of in front, closer than the Fraunhofer distances. It's not this distance was sort of made up for a long time ago, so it's not precisely that metric we should utilize, but it sort of give an indication of that when you're closer than this, you can see these benefits.
So using like arrays on both sides of the link, even in line of to do spatial multiplexing, even in line of sight conditions.
Yeah, and one way of thinking of it also, that the signal that comes from one of the transmitter antennas now have a beam width that is perceived to be small enough so that it sort of give these variations over the array as well. And when we are talking about MIMO communications over a point-to-point link, we often are using the singular value decomposition to determine how we should transmit the different signals. That could describe, for example, transmitting in different angular directions. But more generally here, it just describes what we call eigenmodes, different ways of transmitting in order to create something that is resolvable at the receiver side. And how it looks like in near field, that is something that a lot of people are doing research on.
Right, and that also brings us back, I think, to this point of what is a beam, right? And incorporating like geometry or relying on a geometric model and pretending that a beam is just a ray that you shoot into some particular direction in space, whereas really that's only true if you're far enough away from the array. Yeah, it's an interesting topic, I think, with many more things that could be said. And there's one thing here I believe could be a good place to address, namely a question that I was asked once some time ago by a colleague. And the question relates to coherence of a channel. And then we have the notion of coherence time, which, there are different conventions, but one convention I think we can agree on is that coherence time is the time it takes to move half a wavelength for a given carrier frequency, right? And then the question is now, suppose that we build an array, a uniform linear array, say, with, let's say, M, the mic, elements, and then we know that this array can focus power in space, in beams, and we also know that the beam width in angle, in terms of angle or in degrees or radians, say that beam width goes inversely proportional to the number of elements. So this is 1 over m. And then the question is, now if we make this array larger and larger and larger, right, then what happens is that the beam will get sharper and sharper and sharper, so narrower like this. So could it ever happen then that the beam becomes so narrow that we, during the course of a coherence time, would travel into the beam and then out of it again, which seems to, I mean, if that were the case, right, it would like contradict the notion of coherence time, because we're taught in the MIMO, say, from the MIMO theory, that it's enough to estimate the channel once every coherence time. But if this were true, that you could actually move into the beam and then out of it again in a time which is shorter than the coherence time of the channel, then it would be impossible to estimate the channel with a periodicity or with a frequency of the coherence time and learn the channel accurately enough so we can actually form this beam. Maybe you want to answer it, Emil.
So there are several different aspects to this. One of them, which I think you also have in mind, is that the angular beam width is getting shorter and shorter, but then as you make the array larger, this Fraunhofer distance, or the point at which you can start to see a beam when you are sending your beam towards the far field, that one is also moving further away, and that is contradicting the effect, so that once you see this beam, it will still not become so sharp in terms of the length in wavelengths that it's happened.
That's exactly the point, right? I mean, the beam width in degrees or radians scales as 1 over m number of antennas, whereas the distance you have to be away from the array to actually see anything that looks like a beam scales proportionally to m. So 1 over m times m is equal to 1, right? Which means that in meters, the beam width is at that point going to be more or less a constant and doesn't shrink.
Yeah. But then the other aspects to this is also that you could, if you focus your signal at a point that is in this radiative near field, and then I like to call it a finite depth beam. One can call it different things, whether it is a beam or not, but that one will actually also in radians have the same beam width, which means that the actual length of the beam in the width dimension will be rather small. Yet, one can show that it can never be smaller than something that is proportional to the wavelength, because at the end of the day, it's sort of signals that come from different directions. They meet at one point, and then they should start to move and away from each other and create that the signal are not adding on top of each other anymore. And I think we made the computation in the paper that in the absolute worst case, when you move the wavelength divided by 8, you will lose half of your power, and it can never be worse than that. So it doesn't go to 0 or anything.
Yeah, so there'll be a lot of details here which I think are more easily explained using some visual aids perhaps and mathematics, but in any case I think we did resolve I call it the coherence myth, this fact that the beam actually doesn't get narrower and narrower so that you can't move into it and out again in a time shorter than the channel coherence time. So returning maybe to, we talked earlier about using antenna arrays at both ends of a link to do spatial multiplexing, to transmit more than one data stream at the same time. Is that in any way related to OAM, orbital angular momentum, which I know has been, people have looked at, I think, both from physics community and also comms theory community? To me, they seem to be kind of the same thing, but do you want to elaborate a little bit on this?
Yes, I think this is a example of this. So now when you know that you are so close that you can resolve properties of waves that you are not seeing in the far field, then depending on what kind of array geometries you're selecting, these eigenmodes that I was alluding to are looking differently. And this is an example where you at the transmitter and receiver, you have circular arrays with discrete antennas around them. And then you position them in a particular way, and you are determining how does this eigenmode, the optimal way of transmitting, look like. And then it turns out that this is matching with something that we call orbital angular momentum, and which is some kind of twisted wavefronts. And this is a physically beautiful interpretations of how the signals look like. But it's nothing different, as far as I can understand, from how you would do communication without such a physical model. We sort of come back to the same thing. We can always measure the channel, and we can do MIMO theory on top of it, and it will work out. This is more of a geometrical model of a very different kind of what happens. Do you agree?
Yeah, I think that's entirely right. I mean, so OAM is a particular instance of point-to-point MIMO, where the arrays are located in the near field of one another, and such that you can transmit through spatial multiplexing more than one stream, right? And there's nothing here from a comm theory perspective which is exotic at all. In fact, I mean, the channel between any pair of antennas here is linear and time invariant, and you measure it appropriately, and then you apply the standard MIMO textbook formulas for beamforming or singular value decomposition or water filling, whatever, and that's it. Then obviously one can, with, let's say, an adequate background in physics, illustrate what's going on using this notion of twisted waves and beams or lobes that are very colorful and nice shapes. But there's nothing here that really can't be understood and explained by the conventional point-to-point MIMO theory. Now, considering the fact that the two arrays are actually in the near field of one another, in the array near field or geometric near field, right? So the antenna elements are still in the not closer to each other than they are in the radiative field, so they don't couple too much. But the arrays are in the geometric near field of one another.
Yeah, and there is a lot of related kind of research going on also with people looking at arrays of different types, their different shapes, and try to figure out, can we get a geometrical interpretation of how these eigenmodes should look like? Okay, if we're not sending angular beams in order to reach each other, what should they look like? And what will then be the reason for that? Well, not to improve capacity or anything like that. Maybe it's more about, if you like to make a design that is based on geometry, then what geometry should you utilize? And that is what the research is more about. And yeah, if you do beamforming without knowing the channel state information from the beginning, what dimension should you explore? This is the only thing it's about.
Right. Yeah, that sounds like an exciting direction of research. They could give a lot of insights, right? I mean, as you know, I'm very much in favor of using accurate physical models and also geometric models, obviously, and so forth. But again, as I think we talked earlier, it's difficult to really have a good physical model once you have like anything else than free space line of sight, right? I mean, you got objects here, even just objects. If you put this, antennas in this room here, there are like countless of small things that will scatter the wave, and we don't know where these are, and we will never have enough signal to noise ratio to accurately locate where each one of them is and compute or estimate the characteristics of each one of them. And then at some point, I think we will have to transition to more like some kind of data-driven approach where we just learn what does the channel responses look like right now, or as a function of the position in the room and so forth.
Indeed.
All right.
I have maybe one last thing to add to that, and that would be that, when you are using this kind of data-driven approaches, if you know something about the geometrical world, it could be good to try to feed it in from the beginning. And as you were saying, it will be very hard to know exactly where these objects are and everything, but it could still be that we could tell it that, here are the different dimensions where the channel could exist. And then there is typically a null space, some dimensions that can't exist due to the array geometry. And if we feed them with that information as well, that is helpful for learning.
Certainly. And I mean, if we could deduce where this null space is from geometric considerations, that's obviously great, right? But I think my point was rather that probably in practice you could build algorithms to just learn where this null space is and what it looks like and how large it is and so forth. I'm just thinking back at other problems in engineering, computer science, where we have tried to model extremely complicated, like natural a picture, right? I mean, just a photograph or a shot in a video or something. And I guess in the rather early days of like computer vision, people were like trying to model features. You recognize a face because the face is like maybe a circle or some kind of elliptical shape, right? And you got the eyes are two circles, and then try to figure out where they are and so forth, or detect that there are circles and so on. Well, that only worked to some point, and what really turned out to work are these deep neural networks, right? That really make substantially no prior assumptions at all on what the objects, no geometric assumptions at all on what the objects look like, right? And it's very possible, I think, that once if the goal here is to resolve fine little details in the propagation environment and rely on these details for like positioning, for example, that the inspiration to get there might be from the computer vision world and using these neural networks to learn. But obviously, that said, I concur. I think you brought it up several times that, if you know something about the geometry, obviously do exploit it, right? So, yeah, okay. Right, so that I think covered very much, I believe, what we had like planned to cover.
Yeah.
It's been a great discussion, Emil, and a great deal of important matters here to consider and to learn. So I think we'll be wrapping up here for today.
Indeed.
Okay, so thanks again, and thanks to our listeners, and don't forget to log into YouTube and like and subscribe us there. So with that, until next time, bye-bye.
Bye-bye, thank you.